Okay, good morning everyone. My name is Christopher Dahl. I'm the Virtualization Tech Lead in Linaro. This is Mark Singer from ARM. We co-maintain KVM for ARM and ARM64 in Linux. And today's talk is mostly about architectural evolutions as it pertains to KVM. So just a few words on basically where we are in the landscape. So we're getting really close to being done with what we call sort of the key enterprise features for KVM. So stuff like debugging, migration, PCIe support, and basically being spec compliant with the virtual machine spec that we wrote up a while back. So the two big things that are sort of coming are pass-through, device pass-through, and basically we need to really improve on testing and validation. So those are sort of the key focuses coming up. And then the rest of the talk today, you're free to ask any questions about status or wherever we are with anything later. But the key talk today is about 8.1 and the architectural evolutions there. So I'm going to hand that off to Mark.
Thank you. Well, feel free to come forward. You're more likely to be hurt if you're staying in the back. So I'm Mark Singer. I work with ARM. And yes, as Christopher said, this is mostly about evolutions of the architecture with 8.1. So I'm going to have a look at the virtualization extensions in general, how they are defined since the latest revision of ARM v7, how KVM on ARM uses that, and also how the architecture is evolving and what does it mean for KVM itself. It's going to be a fairly short presentation, but it can be a bit dense. So if you have any question at any point, feel free to raise your hand. So that's the ARM v8 privilege model. v7 is fairly similar with a couple of nits, mostly historical. So this privilege model supports two execution modes, 64 and 32-bit. Interworking is only defined at the between exception levels, so you can't switch from 64 to 32-bit while staying at the same exception level. You have to transition. So the 64-bit mode is always of higher privilege than the 32-bit mode. For example, you can have a 64-bit hypervisor and a 32-bit guest. You can't have it the other way around. It's very important. And from a hypervisor or from a secure mode point of view, the 64-bit state you're looking at is always inclusive of the 32-bit state. So if you have a 64-bit hypervisor, it doesn't matter if you have a 32 or 64-bit guest, its state is always represented the same way as a 64-bit state. Makes it a lot easier to write hypervisor. So on this picture, on the left, you have what we call the non-secure mode. On the right, the secure mode. Typically, when it comes to virtualization, we only care about what's on the left. We mostly ignore the secure mode except for enabling virtualization itself. So the virtualization extensions themselves. So been introduced a while ago now with the latest revision of the v7 architecture. So basically A15 and A7 time frame. So we get a new execution state, EL2 or hype. So EL2 is the v8 name. Hype is more the v7, but you can use them either way. So it's in the non-secure world, has a higher privilege than EL1. It comes with a number of features. Second stage translation. You can think of it as a second MMU, a second set of page tables. So that gives you an indirection between what the guest sees as its physical memory and what is actually the physical memory. It's double level of virtual indirection. So that's basically nested pages. It exists on most virtualization capable architectures. Nothing new here. We haven't reinvented the wheel. Has the property of having TLBs tagged by virtual machine ID, which means we don't have to flush TLBs, extremely efficient. So if you think that we are lagging behind on with x86, no. I mean, x86 just got that. We've had that for forever. So we can decide to trap on accesses to most system registers on a fairly fine-grained, well, more or less fine-grained. Never enough. The hypervisor can really decide what it wants to trap. You have the freedom to decide how invasive you want to be for the guest. In hype mode, you can handle interrupts, fast interrupts, and aborts. For example, the guest never sees a physical interrupt firing. We can inject an interrupt in the guest, but it's never a physical interrupt. So the guest can request for power virtualized services. You can call into hype mode with the HVC instruction, which has been added for that purpose. That allows power virtualized services. For example, that's how we implement PSCI in KVM, so we can boot secondary CPUs. And the standard peripherals, namely the GIC and the timers, have special features to help with virtualization. So on any A7, A15 platform, for example, you have these features, except if you have a Raspberry Pi 2, in which case you're screwed. So EL2, it's not a superset of EL1. It's basically an orthogonal mode. It allows you to multiplex several EL1s on the same hardware. So it has its own MMU settings, its own translation regime, which is broadly LPAE on V7, with a couple of small differences. Has only one TTBR, translation table based register. So that's how you define the root of your page tables. So the effect of this of having only one TTBR is that you can't run the kernel at EL2. It's way too invasive. Can't even represent what is user mode in that case. So instead of trying to change Linux, rewrite it entirely to make it fit in EL2, we just use EL2 as a way to context switch between a host and a guest. So that's for KVM, that's how we use it. For Zen, for example, slightly different. Zen runs entirely at EL2. It can switch directly between guests. So for KVM, for a host hypervisor type 2, the host is actually a form of specialized guest. So that's the general architecture. So you see at the bottom, we have the switching code running at EL2, the white box in the middle, host kernel, with the bit of KVM in there. The host has its own user space, and then on the right of that, you have the VMs with a guest kernel, guest user space. So whenever we decide to execute a guest, we save and restore a lot of things. So stage 2 translation table, trap configuration, our registers, floating point, all the system registers, the gig configuration, the timers. So it's not necessarily all of these, but a number of these points are going to be touched either on the save or on the restore path. And because we switch 2 OSs running at TL1, each run of a guest is actually itself a save and restore. So we start by saving the host context, restore the guest context. And whenever the guest exits, we do it the other way around. We save the guest context, restore the host context, go back to the host to manage the exit reason. So as you can see, it's fairly simple. It's not too bad from an efficiency point of view, but maybe we can do a bit better. So that's the marketing slide. So ARMv8 evolves. It's not a fixed architecture, and we recognize that there's always more things to address. So the new v8.1 revision comes with a set of new extensions. So we have new atomic instructions. We have new SIMD instructions, some memory management improvement, performance monitoring. We have larger VMIDs. On v7 and v8, we can have up to 256 VMs running at the same time. I insist on the running at the same time, really. With 8.1, we can have a lot more, 16-bit worth of VMIDs. That's just enormous. And also, we have the virtualization host extensions, which are designed for type 2 hypervisors. And yes, that is extremely interesting for KVM. So what do we get? We get an improved EL2. So this new EL2 is designed to, as I said, to improve the support of type 2 hypervisors. It allows the host OS to run at EL2. So when I said earlier, we only have this one TTBR0 EL2, which prevents us, among other things, from running Linux at EL2. But that restriction is removed. So the host OS requires very minimal changes to run at EL2. User space is at EL0. So you end up with a gap in between on the host. Nothing runs at EL1 for the host. The guest OS still runs at EL1. Nothing is changed for that. And this is ARch64 specific. There is no support for host ARch32. You can still have ARch32 guest. That works perfectly. In this mode, EL2 really becomes a superset of EL1. That's exactly what we need to support KVM, basically the host kernel running at EL2. So, like any architectural extension, you have to be extremely careful with preserving compatibility. And then that's exactly what we've been looking at very closely. So one of the major design goals were to make sure everything is discoverable. So you have feature bits that you can probe to find out what the core actually supports. It allows the EL1 software, so your host kernel, to run transparently at EL2 with hardly any modification. Of course, something has to give in, which means it's the virtualization software which will be impacted by the changes. But that's fine, that's why we're here. So when the virtualization host extensions are in use, most EL2 system registers can actually be accessed with their EL1 accessors. They are transparently upgraded. So in this example, if you want to access the translation configuration register, you will use the EL1 accessor at EL2 transparently, like you do it today in a V8 kernel. But that will effectively access the equivalent register at EL2. And if you're a hypervisor and trying to context switch that same register at EL2 on the behalf of a guest, then you will use another register called TCR-EL12, which means the EL1 register as is from EL2. Slightly confusing, but it's the best we could come with, naming-wise. I could come with much worse. So a consequence of that is that the kernel mostly runs unmodified. That's really good. It means we're going to be able to take a single binary and move it to EL2 on the core supporting the v8.1 architecture. It will just run. The drawback, of course, is the virtualization software has to be relatively heavily modified. So, for the kernel itself, so if you remembered, I go back a bit, it looked like this with V8. So we see the host kernel at EL1. If we go back here, the kernel has moved to EL2. On the left side, we don't have anything running at EL1. There's really a no man's land here. User space is where it should be. And the guest is exactly like we had before. Nothing's changed. So what do we have to do for the kernel? Basically, we prevent the kernel from downgrading to EL1. Instead of normally on the V8 kernel, you enter the kernel at EL2, install some stubs, go back to EL1, you're done. Here, we're just going to stay at EL2 forever. We need a new debug configuration. That's one of the few changes we have to do. We're going to transparently use the hype timer instead of the guest timer. So for those who've looked at the timer recently, there's 4 interrupts. There's 4 timers really. There's a physical timer, secure physical timer, non-secure, a virtual timer, and a hype timer. So, being non-secure, we don't use the secure timer. KVM uses normally the physical timer, gives the virtual timer to the guest. Here we're going to silently upgrade our physical timer to be the hype timer. We also gain an extra one, which is the hype virtual timer, but we don't use it for KVM. The transparent upgrade is exactly what we need. A slight consequence is that the interrupt use is different. So we have to cater for that. And that's it. That's really it. It's really it's literally a couple of lines to change in the host kernel. For KVM itself, it's much more invasive. So we have a new way to enter the switch code, a new way to address guest system registers, as we've seen. Also, a small consequence is that we now have to switch the vectors depending on the role we're playing, either as a host or as a hypervisor. So it means that we changed vbar EL2 between the host vectors and the hype vectors, depending whether we're running the guest or the host. So what do we have to change? Really the impact. So we reduce quite a bit of system register churn because, as you've seen, a number of registers have now been upgraded to their EL2 counterpart. It means we don't have to save this register when we enter a guest. The host registers are preserved by virtue of being at a different exception level. We're really down to 4 registers being shared, or the thread-specific registers, and ACTLR. So it means we can implement a lazy save restore policy for the guest as well. If you're running a guest that traps for any reason, that exits, there are a number of cases where you can go back to the host, process that exception, and resume that guest without doing any save restore of its system register context. You just have to switch these 4 registers up there. It's an improvement, really. We also can reduce the physical interrupt latency. If you remember how it worked on V8, when we get an interrupt, we have to exit the guest, which means saving its register, restoring the host registers, and only at that point we can start handling the interrupt. With V8.1, we still have to do all that work, but we can delay a number of the save restore operations. What we can do is actually save, for example, the general purpose register for the guest, restore those 4 system registers, and at that point we already have enough context to start executing our interrupt handler. Which means on the return of that interrupt handler, we have to continue our world switch and finish our save restore. But we've reduced the interrupt latency by moving that interrupt handling a bit earlier in the chain. Another thing is that we don't have to trap to enter KVM. It's always good not to trap. It's just a normal function call. Oh, well, we don't have any hype mapping anymore, so for those having issues with kexec and KVM, that problem doesn't exist anymore with 8.1. And of course, the switching code in hype has to be heavily rewritten. And we're going to get to that now. So we want only one single kernel binary. We're not going to go back to the dark ages of the 32-bit kernel where we had one or maybe several kernels per platform. We are multi-platform and we're going to stay multi-platform, and that includes having the same kernel across multiple versions of the architecture. And of course that includes KVM. It's not because you want to support V8.1 in KVM that you're going to have several kernel binaries. Which means we have to pick the right code at runtime. And for that, we have 2 complementary solutions. One is testing feature bits, or checking the mode we're running in the kernel. So if kernel is in hype mode, then do this. Otherwise, do what we used to do. It's fairly simple, very straightforward. Just have to look at that code and you know what it does. Except testing stuff on a hot path is not very good. We're trying to keep performance at its best, so that's probably something we can only do on the slow path. So far, the fastest approach we've taken is to dynamically patch the kernel at runtime. So we now have a way to detect features in the kernel and to use alternatives for certain instructions, certain code sections that we dynamically rewrite when the kernel boots. It's on the scary side of things, but it proved to be quite nice in the end. So we end up with constructs like this. So this particular line, if VHE, is actually directly taken from the V8.1 hype code. So if VHE is actually very badly written, because what you have on the left side is the V8, and on what you have on the right side is V8.1. So it should be renamed to something easier to understand. But you're seeing that on the left side we're accessing the TCR-EL1 while saving possibly the guest system register. For the V8.1 we're accessing TCR-EL1 too, indicating yes, we're in hype, and accessing the EL1 register. So depending on the CPU we're going to run on, that code is either going to stay unmodified with the version on the left for V8, or patched with the version on the right if we're on V8.1. So it's very efficient. It's very good for the fast path, the hot path. Yes, it's harder to maintain. It's less readable. You have to get used to read 2 code paths at the same time. And it's mostly for assembly code. which is how we write most of the hot path. So where are we with that? So it's still a work in progress. And well, there's two versions of that. There's the prototype, which is based on 315 RC3, which it's a horrible piece of hacks. It can't run. You can't run it directly on. It forces you to have several binaries if you want to put it on V8 or V8.1. It's basically used to evaluate the architecture, and I fully intend to remove all traces of that code extremely soon. It's basically non-maintainable. But we have a new branch for that, which is based on mainline and rebased almost every day. That uses code patching extensively, runs on the fast model, and will hopefully being available soon when posted publicly once it's gone through the necessary internal reviews. And I think that's it. Any question? Stunned audience. Perfect. That's absolutely for Al. Can you? So I'll repeat those questions, or maybe you can say it again.
So are you actually directly modifying the text pages as you boot?
Yes. So we are actually patching the kernel text whenever we boot. So we start by detecting all the features. Wait until all the CPUs have booted, check that they are all the same versions and all that, that all the features apply. At that point, we do stop machine. We have a number of text sections in the kernel, and we repaint the whole thing, invalidating the iCache as we go. And so for this work, we patch about 70 instructions, 70 code locations. It's extremely fast. It's also how we handle errata workaround. It's the exact same technique. And actually, that code patching technique was initially used for that. It's already in mainline. I've just extended it a bit to handle things like branches in the middle of a patch section, which is always a fun thing to do. And yeah, it's really nice in that respect. Victor?
So it's it's more marketing question, actually, maybe. Is there any existing hardware that support 8.1 already, or if not, when do we expect to see just approximate time frame? So on the real hardware.
So to the best of my knowledge, there's no hardware available with this at the moment. It's very recent. You have to realize that. So I'm not privy with any roadmap, so I can't really comment on that. But so far, I'm not aware of any existing hardware.
Thanks for the update on the new architectural stuff, Mark. But maybe it was not intended for this session. Were you going to go over at any point the status of VFIO?
So we can talk about VFIO as well. So that's completely unrelated to this. So VFIO is now functional on, well, VFIO PCI, to be precise, is now merged and functional on ARM. We have all the bits and pieces merged, with the exception of the MSI support, which is still a work in progress. There's a number of patches on the KVM ARM and general Linux kernel mailing list to support VFIO platform and the VFIO maintainer, which you have to realize that VFIO is fairly unrelated to KVM. KVM can use it, but it's a separate subsystem. The VFIO maintainer is still reviewing the VFIO platform patches from virtual open systems. That's making some progress. It's not completely there yet. There's also a number of patch series coming from Eric, who's in the back over there, dealing with interrupts, RQFD, and all that. We now have most of the pieces there. It's more a matter of finishing the review, getting the last bits and pieces done, basically polishing it. But the core stuff is already there. Or maybe you have something to add?
I mean, the only other thing to add is that PCI Express support is coming to QEMU, any day now. So all the standard pieces you'd use, the patches are there. I think they've been reviewed and close to get upstream. So all the pieces you need to use is basically getting into the right trees. So, but maybe for the networking stuff, you want to look at it's for platform device pass-through, right? And that stuff is being worked on, and yeah, it's really close.
Thank you. One other question. And pardon me, I'm not that close to the development, but I had understood that there was a lot of work going on to deal with some issues around VM migration. Could you tell me what the status of that work is?
Yeah, so we basically have it working. There was one bug that we're still working through that was quite difficult. We spent a month on or so, and I think we've nailed it yesterday night. So yeah, it should go upstream soon. So as I introduced to sort of this talk, was that the overall status is that those features that we've had listed as sort of the things we needed to do to be feature complete for what we know to be the use cases in the networking and enterprise segment. Those are the things we're working towards as our prime focus, and those are the things we're trying to get done as soon as possible. And it really isn't this, like right now in this quarter that we want to get those things done. So we're still missing, after migration gets merged, we're still missing debugging support and performance monitoring. People use that, and PCIe pass-through with VFIO. But you know, as Mark said, they have it working. So it is just a matter of getting the last bits upstream. So we are really close.
Yeah, so to be complete on the PCI story, we have it working with KVM tool on an ARMv8 platform, the AMD platform to mention it. It's working nicely now. In KVM tool being mostly a prototyping environment, I'm really looking forward to the equivalent patches being in QEMU for completeness. And yeah, I expect that to be there pretty soon.
Thank you.
All right. Any other question?
Just can you give some example about this short actual enter in AL2, do actual job quickly and then actually come back? Would be like PCIe interrupt injection one of those? What other things actually you have in mind?
Sorry, I didn't get the question exactly. About the...
So you talk about that now instead of like two context switches, and you can have lazy actual register actual saving, and basically kind of how much functionality actually you will do. So basically, is it kind of pass-through would be actually much better on 8.1?
So that's not going to change much for anything like pass-through. You still have the exact same interrupt handling features. Well, you still do the same things. It's just that you have some code path can be shorter, and because you have banked registers between the two exception levels, you don't have to do as much save restore as you would do on V8. But that doesn't affect anything with respect to device pass-through or things like that. You get somewhat better performance in your context-rich path, but that's what it's about. Has no visible impact on device pass-through at all.
Yeah, I guess the way I would look at that is that, per definition, when you're running virtualization on virtualization supporting hardware, the overhead you see is the time obviously not spent in your VM. Otherwise, you'd be performing the same as your host, right? So that overhead comes from two things: the time spent actually switching to your host and the work done in your host. Right? So the work that's done on your host or in your hypervisor, that will be the same, but the time spent switching is pretty considerable right now, and that will be potentially much shorter. It would depend a bit on your workload, but yeah, for things like handling an interrupt that hits from a pass-through, an assigned PCIe device that will hit on your hypervisor, you'll trap to your hypervisor, you'll grab that and you'll inject that to your VM. Since you're not context switching into any other VMs or doing anything else, the state that you have to context switch will be much, much smaller. And I mean, we don't know, but if we go and measure it once we have hardware, I would be surprised if we don't see a huge benefit there.
Yeah, so it's also worth mentioning that, well, it's something you've looked at in the past, is that a lot of the time we spend context switching is at the gig level, especially when you have an MMIO mapped gig. It is likely that moving to gig v3 will have slightly better performance. It's certainly visible when you have a gig that is quite far away from the CPU cluster when you have to go through an interconnect. I mean, doing this traffic can be a bit slow. Certainly with system registers, we are likely to see better performance as well. So, I mean, as always, you can't just consider the architecture bits. You have to look at the system overall and see where you're actually spending your time and if that matters or not. Really.
We should probably clarify that the numbers that we do look at, it looks pretty good. I mean, even considering the work that we're actually doing, Zen is more optimized than KVM for the way that V8 looks now, but none of it looks really bad. I mean, if you compare to state-of-the-art x86 stuff, KVM, we're doing all right overhead-wise. So, you know, we do believe this is a very viable system software approach.
You mentioned at the start that you're going to talk about testing. What exactly do you mean by testing, and how, what, etc.? You know, and is there anything else that other people can do with regards to the testing? Have you got a test framework, etc., and stuff like that?
So this is really one of our sort of our Achilles heel, and it's an area where we should be doing a lot more. So right now, testing of the KVM implementation itself is pretty much what me and Mark have time to do on the devices we happen to have available at any given moment. We do have some things running in Linaro's you know, set of tools. There are some builds in its CI framework, and there are some things running on its Lava system, but it's not monitored properly because we don't have the tools for it. And it's a thing that we've been trying to improve on for a long time, but unfortunately I don't have the resources in my team to build that exclusively. And I think it's a problem where we have a problem in Linaro and this across the board for kernel testing. And it is sort of a very broad problem that's just hard to attack. So Kevin Hillman from the kernel team is doing something with some of the Lava guys where they're building another tool, and that's looking really promising, but they could use a lot more help. So what I've been doing from a virtualization point of view is to say, well, if you don't have basic kernel testing, then I have to invent basic kernel testing to test KVM because KVM is part of the kernel. And that's just, it's a little bit out of my focus, basically. So what I'm doing is I'm trying to help them as much as they can and hoping that will amount to something. And then what we need to be talking about and what we need to be doing is that we need to build whatever you need on top of your basic kernel CI framework that boots on various devices that can actually run VMs and run workloads within VMs and run tests as in KVM unit tests and basically running standard Linux tests in VM guests. So we should say that we've had some help from Red Hat as well, who've actually ported the KVM unit test framework to ARM64 and added SMP support and stuff on that. And that's an area where we can jump in and begin to add tests now, and that's one of the things we will be doing once we finish the sort of the feature completeness. But even if we do that, we still don't have a framework to constantly monitor that. And what I would really like to see is whenever we queue up patches, we get patches from anyone, we should be able to push that to a queue somewhere before actually merging it, or at least when it gets into next, and it should be tested on a commit by commit basis, and we should get feedback that tells us, you know, this commit is degrading performance by 10%, stuff like that. But we don't have the tools today. So it's not a very positive answer, but it's the best we can give.
Have you got suggestions of what tools to use for checking performance regressions?
Tools to use for checking performance regressions. So there are a number of... So I simply haven't had time to look at the existing tools in details. There are some from both Citrix that use it for Zen, OSS tests, OpenSUSE runs some things. Red Hat obviously have Autotest or Avocado, or what it's called today. But those are big frameworks that take, you know, time and energy to get into and set up.
Things as simple as running LM-bench in a guest, for example. Tracking Hackbench is my favorite one. Doing that on a doing that on a daily basis, running LM-bench or Hackbench on a daily basis in a guest, preferably in the same guest, not changing everything at the same time. That'd be really, really interesting. And I had a lot of hopes about Linaro being able to deliver that 2 years ago, and my hopes have slowly evaporated. But I'm definitely there's some really, really good effort from Kevin Hellman with the kernel CI work, and I mean at the moment they are only testing bare metal, but they are in virtualization being able to boot a KVM guest as part of their let's boot everything on this planet. That's really good. They're planning to tackle virtualization as well, and maybe Zen as well, hopefully. But we need more than that. We need actual performance tracking, regression tracking, and so far we don't have much. I mean, when you look at what the x86 guys have with the O1, the zero-day infrastructure that runs on kernel.org, I mean, it's absolutely fantastic. And whenever I break x86, I know it within seconds. I'm not asking for the same functionalities, but at least, you know, some form of performance tracking. That'd be awesome. So hopefully this kernel CI infrastructure is going to be expanded to do that.
Don't you want to pick up some server, kind of like server-grade actual workload, and simply actually just test actual this performance of this workload, host versus actually kind of KVM stuff, and that's actually, frankly, that's what matters, and that's what we did with the early version actual of stuff.
So I think it's important here to distinguish between, okay, so we have a lot of problems concerning our test harness and some framework to capture our test results. And then there's the other question of which test should we actually run, and we can have a chat about that. But that thing I don't think anybody's really concerned of. It's not, you know, that's not very hard, right? We have a bunch of things we can just go and run, and that's the things we run daily or manually, right? But it's just not monitored. It's not structured, right? We're not notified of things that happens externally and affect us, stuff like that. It's things we just can't do manually, and we're limited by the amount of cycles we have. So the kernel CI work that's been done is basically building and booting, which is fine, but adding any sort of test capturing and then tracking performance over time and things like that, that's what really is missing. And that's a non-trivial problem to solve. Yeah,
I think once we have the infrastructure, it'll be really, well, not trivial, but a lot easier to add, you know, sorry? Are you deaf? No, what I was saying is once we have this infrastructure, if we have it at some point, it will be maybe not trivial, but at least a lot easier to add, I mean, the enterprise or network-related tests you're after. I mean, we have to start from the basics, and we don't even have the basics at the moment. So this is my recurring moaning about lack of testing, lack of infrastructure. But I mean, we're at a point where if we want KVM on ARM to be credible, we need that. We can't afford untracked regressions. That's just not possible. So if we want to be taken seriously, we have to invest time and effort into that. There's no way around it.
And getting the hardware that we should be supported on into the hands of, well, at least maintainers, but also developers would also help with things in general.
Yeah, so that's also a recurring problem, is access to representative hardware. So we get basically two kind of positions. We get some silicon manufacturers that are completely open with us, that give us access to hardware, sometimes under conditions, and we can perfectly understand these conditions, not to disclose things about the hardware, and that's fine as long that doesn't prevent us from contributing patches, continuing our kernel-related work. There are other manufacturers who are much more closed, and basically we can't use their hardware, or we just stop working altogether. So it'd be good if everybody producing hardware would help us to help them. That's a really important message. So if you have a brand new hardware that you want to be sure KVM is supported on, runs really nicely, please come and talk to Christopher and I, and we'll see what we can do.
Okay, so I have a follow-up question to Bob's pass-through question here. So today VFIO assumes an IOMMU and some DMA subsystem, and that's a really nice way of getting pass-through. It the VFIO interface ties into upper-level management software. Great, but what do we do with all these networking SoCs out there that do not have IOMMU, do not have explicitly programmed DMA, or might not even need them to offer secure pass-through? So how can we tie that in? Because I saw there was a discussion like half a year ago from Freescale on the mailing list about extending VFIO to actually support other type of devices that don't have IOMMUs and explicitly programmed DMA.
The question is, how do you ensure isolation?
Yes.
How do you ensure that your device is not going to go wild? That user space, you have to remember, it's user space that controls this device when you give it to VFIO. How do you make sure that this user space is not going to wipe your kernel, to DMA your credit card number on the other side of the planet? I mean, these are real questions about how you ensure security in your system, isolation in your system. And
so
I don't have an answer with the lack of IOMMU, really.
Yeah, so let's say you have a device such as that. We have a device like that. It doesn't have an IOMMU, it doesn't have explicitly programmed DMA, but it's still secure. So how can I use VFIO in order to or
Can
something
you
similar?
You have a device without an IOMMU with devices on there,
Yes,
a networking device, but it is what, still secure?
Yes.
Meaning?
I mean, so you can expose some abstraction up to the guest that there will be networking packages flowing through that.
But is that because the devices are not bus mastering, or?
No, so it's I can talk about it offline, but it's a very different architecture, and many of these SoCs have something similar.
So my comment on this would be, so VFIO doesn't, I mean, it is currently built around the concept of IOMMU groups, because that is the only way you can, I mean, looking away from really fancy hardware that has, that's non-standard, but that is the only way you can ensure isolation in guests. It's almost a trivial thing to add a fake IOMMU to VFIO and say, okay, just pass it through, right? And you can use that with and you could do that safely with a non-bus mastering device, right? So you could just map that into a VM, and you can run 2 instances of VFIO to even map that into user space in your VM and do all that stuff that the networking group wants to do. But yeah, so if you have sort of more esoteric hardware, which is some blend of that, then yeah, we would obviously have to look at the hardware to come up with a solution. But I'm pretty sure we can bend VFIO in a good way to still do that.
So basically
what VFIO gives you is the capability of mapping memory regions into a guest and to route IRQs in the most efficient manner.
So you're recommending a fake IOMMU and then still using the IOMMU group concept?
from the top of my head, I
Yeah.
think that's probably the least invasive change, so you could do what you want to do.
Yeah.
But you know, that, as everything else, you'd have to sort of come talk to us with a specific use case, and you know, we could develop a prototype patch series, post the design review on the open source mailing list, and take it from there.
Okay, good, thanks.
Looks like that's it. All right, come talk to us for offline things then.
Thank you.